So this factor here, I should pull it down a little bit. So what happened overall is that we send messages here from variables to factors. At the next level, from factors to variables, then from variables to factors, and from factors to variables. And now we're not going to derive the algorithm, but let's, motivate it. So one thing, if we look at what these steps have in common, so what happens if we send a message from a variable to a factor? This is, happening here and there. Here's a good example. No, variable to factor, sorry. There's a good example. So what we apparently do when we send a message from, so here we send a message from C to CE. We send a message from this variable to that factor, is that we multiply the incoming messages at that variable. So you see mu was this parenthesis here, and that mu was that large parenthesis, and we multiply the two. So we're now taking a leap of faith and saying that this is always the case. So we take a product over the neighboring factors of that variable, of the messages that the neighboring factor sent to that variable, where neighbor is now defined as all the neighbors of all the neighboring factors of variable x except the factor that we're sending a message to. This notation is a little bit sloppy. So if you look at this statement, it is at least not in contradiction to any of the operations on the blackboard. And next, we can send a message from factor to variable. So here, for instance, here by sending a message from factor ABC to variable C, we have summed out those variables. We have summed out all variables except the one that we're sending to, and then multiplied the native factor and the incoming messages. So we sum over all variables in the scope of our factor except the variable x that we're sending a message to. So in other words, these are all variables that the factor depends on except x, because this is where we're sending our message to. And then we multiply with the native factor, as has been the case here, or as has been the case there. I'm now writing a capital X to say these are all the variables that this factor depends on. And then multiply with the product of the incoming messages. So we have taken all the messages from neighboring variables to this factor, and all except the one where we're sending our message to. We have multiplied them. We've multiplied them with the native factor, and we have integrated out all variables except x. All right, and these two equations define a recursion. So we could say that if we do a few sample calculations like we've done on the right-hand side, we obtain this new algorithm. For message passing on factor graphs. We still need a starting condition, namely what the leaf nodes are sending. So if a variable is a leaf node, the first message it sends to its factor is simply 1. If x is a leaf node in the factor graph, and vice versa, if we have a factor that is a leaf node in the factor graph, simply the value of the factor itself. Taken together, this is the algorithm. So because variables are sending all incoming, or are multiplying all incoming messages, we have a special case, namely if a variable only has 2 connections, like A or B here, then to multiply all incoming messages except the one we're sending to means simply pass on the message, right? So if we want to send a message from A down the graph, it simply passes on the original message. So we could use this insight to add an additional level to this hierarchy here, where we say that we have a message from factor B to the variable B. And because of the property that I've just mentioned, this is identical to the message that we wrote before. And similarly, we have a message from factor of A to the node A, which passes on this message unmodified. Okay, so at this point we can really try out this algorithm. So first we send messages from variables to factors. So we can start either way. If I'm really starting in the hierarchy that I've written here, we would first start with those messages here. Then next, we would have messages from the variables to the factor ABC. So this would be at at level number 2. And also at the same level, we have the message from D to its factor. Then at the next level, we have these factors sending to variable C. At the next stage, we have C sending to its factors, or its factor, and then finally. Okay, this is just the hierarchy that we have here. So these steps that I've written, this would be step number 1, 2, 3, 4, and 5. And remember that we have simply regrouped the messages that we usually send around the junction tree. So just as in the variable elimination algorithm, we can pick an arbitrary route, for instance E, send messages from everywhere to E, and then from E back to everywhere. And then once we have the messages in either direction, we can compute the posterior distribution at any variable. Let's also see what these equations here mean qualitatively. So qualitatively, this first message says how does variable x, let me put an extra set of quotations here, feel about being in state X. And here we have the factors telling us how does the factor phi feel about, to the extent that factors and factor graphs have feelings. Okay, and for inference, just as in variable elimination, we can send messages in proper order. By proper order, I mean sending a message only when all required input is available. To some target node, or you could call this the new route. And from this target node back to all leaves. The marginal of any variable is then given by the product of the incoming messages. Because we've derived our factor graph here from directed graphical models, we need not worry about normalization. The normalization is already correct. However, when you do this on undirected graphical models, then you need an extra normalization step to get out proper probabilities. And the marginal of any factor, if you happen to be interested in that, is given by the product, again, of all incoming messages but also you need to multiply here with the local factor, with the native factor. So why did I insist on working on polytrees? The reason is that polytrees have loop-free factor graphs. So the factor graphs are trees. But as soon as we introduce loops, there will be some nodes that will never have all required input to send their message. So the minimal example, or let's modify our graph here a little bit to get an extra loop. It's not the minimal example, but it's derived from the one that we've just studied. So this new edge means we now have two different paths to go from A to D. So it's no longer a polytree. And I can draw the graphical model that goes with this. So now we have this factor corresponds to the probability of D depending on both A and C. So I have a new ternary factor here. This factor depending on A, C, and D. And let's now start with our message passing. So for instance, let's start at the variable. This variable can emit, and that variable can emit at stage 1. Next, we have factors emitting, so that would be at stage 2. And now we want to have variables emitting, so this would be stage 3. And at this point, we're blocked because these remaining nodes, they can never send out messages, because to send a message, they need input on all edges except the one where they're sending to. Okay, and here we have a blockade of not knowing. So exact inference is no longer possible. So what do people do about this? What is the way forward in science if there's a problem? Or LBP for short. But you anyway need to send messages somehow. So in loopy belief propagation, you can take random initial messages and then keep propagating them either until convergence or until you run out of time. And this corresponds to approximate rather than exact inference. And there are papers by Yedidia and colleagues that show that this corresponds to a mean field approximation. A model that is also known as beta free energy in physics. Since there are so many physicists here, does anybody know that beta free energy? Okay. Okay, and this is one of the reasons for the great popularity of this algorithm. So it applies to directed and to undirected graphical models. If you have a tree-shaped factor graph, your inference will be exact. If not, you can still use it. Actually, there are some variants. So to prevent oscillations, you can damp these messages over time. It would be damp message passing. Or there are other variants like tree-reweighted belief propagation that are better in some applications. So how does this compare to the junction tree? The difference is that the junction tree always produces a tree-shaped graph for message passing. So the obvious advantage is that this will always give you exact inference. Then why does one not do it all of the time? The reason being that these new trees that you produce, they can have large width. And width is here not defined as the number of branches that you find at any given level or at any given distance from the root, but width is here defined as the maximum number of variables that you have in the scope of a factor -1. So the junction tree algorithm, it gives you artificial new factors, as you have seen. The big pluses, can be arranged in a tree. The big minus is that these factors get more and more variables. So especially if you really take an undirected graphical model, let's say as an image processing, you could use variable elimination, but you would get enormous tree widths, and the algorithm then is no longer computationally feasible. On the other hand, you have a procedure that is extremely simple to set up, but that will only give you approximate inference if your graph does have loops, as it would, for instance, for this stud farm example that we looked at last week. All right. So let me just sketch an application on undirected graphical models that is used in image processing. Let's say that we have an unobserved, this is typically used in smoothing an image. Let's say that we have an unobserved true brightness at each pixel of a gray image. These are just 4 pixels out of the very many that an image typically has. Now, for each of these hidden variables or latent variables, you have a factor that is typically coupled to the local observations that you made, for instance, in the original photograph. And this factor will try and let your prediction, your hidden variable, stay somewhat close to the observation that you've made. And on the other hand, you can have factors that argue that, or which try to enforce spatial smoothness between these estimated gray values. And then, since we have a 2D array, this typically goes on and on. Now, exact inference is not possible, but these factors can, let's say this factor can tell that variable what it thinks the true gray value should be. And on the other hand, we have a factor telling that variable what it thinks that gray value should be. However, that factor depends on your current estimate for the hidden variable here, and so on. Yeah? And since we cannot observe these hidden variables, we have this problem of wanting to know them all at the same time, not knowing any of them initially. And this is one example where loopy belief propagation would be used. For instance, you could initialize each of these hidden nodes to the originally observed gray value, and then start having them talk to each other until they reach some consensus. Any questions? So if your factor graph is free of loops, this is much the same as variable elimination, except that we sum out several variables at the same time here. Difference being that variable elimination allows you to do exact inference also on graphs that do have loops, but computation cost may be heavy. And here you have a very simple recipe that will allow you to work on graphs of arbitrary complexity and will at least give you approximate inference if there are loops. All right. Any brains left? I hope so. Because I want to now introduce hidden Markov models. So this is a generative model, a particularly important example of a Bayesian network. In general, this is a model that can be presented in a variety of ways, where you have states which are hidden, and then some observations. So let's say, for the sake of argument, that the hidden states would be if a driver wants to overtake another driver, or wants to continue driving, or to decelerate, to accelerate, or to stop. Those are the hidden states, so the driver intention. And you would then also have some observations. Let's say if the driver has put on the indicator, or if the driver depresses the gas pedal, and so on. And one possible application of hidden Markov models is to try and infer this hidden state from the observations that are available. Now, since it's a generative model, I can try and explain it in terms of a transition diagram. In which the different states would be that the driver wants to overtake, or the driver wants to continue as before. The driver wants to decelerate, or stop, or accelerate. So let's say the driver, if the car is initially standing, then we can simply remain in that state. So the driver is stopped, and the driver wants to continue stopping. But the driver can also, being stopped already, you cannot decelerate, you cannot, not overtake immediately, but you can accelerate. And you can either keep accelerating, or you can, once you're fast enough, decide that you merely want to continue, or you may decide to overtake, or you may try to decelerate and stop eventually. once you're going at normal speed, you could either want to go even faster, so accelerate some more, or you could decelerate, or you could even want to overtake. Or you might just want to continue as you did. So overtaking can take a little bit of time. Once you have overtaken, you might want to continue at normal speed, or if you were going too fast, you have decelerated a little bit. Once you've reached your target speed, you might want to continue. So that would be a transition diagram where, in this case here, the hidden state would be the driver intention. And the observations could be whatever the car electronics offer you. So could be the fact that the indicator is set or the gas pedal is depressed. You might even have some GPS information and some roadmap, etc. And so let's say, given these observations, you want to estimate the driver intention. For instance, to feed the engine with the appropriate amount of gas that it may require at that moment, or let's say if you have a door opening mechanism, you wouldn't want to allow opening the door while the driver is about to overtake, or can think of probably there are easier ways to implement that specific functionality. But so for collision avoidance and so on, this is of interest to try and predict what the driver plans to do. So we could now, it being a generative model, we could now create a series of hidden states. So for instance, we could start at stop, and after a while the driver accelerates and then continues, and then wants to overtake, and then continues, and then decelerates, etc. Or the driver may be stopping much longer initially, then accelerate only a little bit, and then decelerate and stop again, accelerate, etc. So this is like a game that you can play. You have some finite state automaton, and you can move from any of these states to the next, where these transitions are governed by some transition probabilities, which we will later denote by some matrix A. So for instance, this would be the transition probability from continuing to overtaking. Now I will draw in total 3 pictures that all correspond to the same example here. The next picture I'm drawing, because this one here, it has no notion of time. So the next depiction that I'm giving takes time into account. So I have the overtaking and the acceleration, the possibility to continue or to decelerate or to stop. And whereas the first was a transition diagram, the one that I'm drawing now is called a trellis or a lattice diagram. Because I have this lattice of states here, which continues, and now I have an explicit notion of time I have time n, n minus 1, n plus 1, and so on. Now I can here indicate these same transitions. So from overtaking, I could either continue to overtake. So in each of these states, I have these self loops. Those are easiest. These self loops in this picture are just straight lines. Now, apart from staying in the overtake mode, from overtake I can go to continue, and I can go to overtake from accelerate. Now, accelerate also allows to switch to continue, and continue allows to go to accelerate. Then I even have a connection apparently from accelerate to decelerate here, but not vice versa for whatever reason. And from decelerate I can continue. From continue I can decelerate. And from decelerate I can stop. Now the only possibility to get out of stop is to accelerate. Okay, starting to get messy. Now we make here the strong assumption that the transition probabilities, they are assumed constant over time. So I will have the same, so the topology, the arrows are going to remain the same over time, and even the transition probabilities themselves will remain. Now this picture only reflects the topology. So for the next time point I can simply copy this now. Ist ganz falsch. How can you tell it's wrong when you can't even read anything? So I think you get the idea, or I hope you do. Now, a third representation of the same is in terms of a directed acyclic graph, where I have a hidden state which are omitting observations. And you see that we have a lot of conditional independence assumptions here. So what this model tells us is that the observation at time n only depends on the hidden state at time n, and is conditionally independent of the rest. And hidden state at time n is conditionally independent of everything, of all former states, if we condition on z n minus 1. Okay, because I have no arrows coming from somewhere further in the past. And because the graphical model is so sparse, so because it has so many conditional independence assumptions built in, this is the reason why inference in this model becomes tractable. So we have all three are equivalent, but this is the framework that we know by now, and we are after the break going to study on one hand questions like what is the probability of all observations under a given model. So for example, we might want to see which of two models better fit the data. So we want to know what is the overall probability of all observations under a given model. And we can even learn the parameters of this model. That'll be a lot of math after the break.
Die sind abhängig nur von der relativen Lage im Intervall. Sonst müssten Sie nämlich, wenn Sie es anders machen würden, müssten Sie für jede denkbare Kombination von Intervallgrenzen, müssten Sie immer andere Koeffizienten ausrechnen. Das wäre natürlich Quatsch. Klar, also die klassischen Methoden, die wir auch behandelt haben, sind die sogenannten Loop-Codes-Formeln. Das sind jetzt spezielle, man wählt TI äquidistant. Also Sie fangen an bei sozusagen T0 ist Ihr A, wenn H gerade W minus A durch N und dann kommt allgemein Ihre TI heraus als A plus I mal H. Entsprechend Tn ist dann B. So, das sind die New-Codes-Formeln. Die kennen Sie auch, aber das frage ich Sie nicht. Wie heißen die denn? Oder können Sie sagen,